Okay, so then let me move on to the last thing that I wanted to cover today. And I learned this as an undergraduate in an electrodynamics class. And to be honest, it blew my mind. So yeah, anyway, but before I do that, let me take 1 minute and refill my cup of coffee, okay? So there's a deep connection between propagators and causality, and that comes from considering the differential equation that is satisfied by the propagator. Okay, now recall that the propagator essentially describes how the state alpha x of t evolves in time, right? And therefore, k x of t, comma, or sorry, semicolon, x prime t0 must satisfy Schrodinger equation. In the variables x and t. Okay? Because alpha, because alpha x prime t0 is just the initial condition. But there's a subtlety, okay? And the subtlety comes from these two observations. In the limit where t goes to t0, the propagator x t x prime t0 just becomes, x prime, and therefore this is just delta cubed of x minus x prime. And remember that the time evolution operator, when t goes to t0, in the limit t goes to t0, well, I've already put 0 here, but it should be really in a more careful way. This just becomes the identity operator. So these imply that the propagator k satisfies Schrodinger equation with source, meaning that if I apply the Schrodinger operator, this is the Schrodinger operator. If I apply the Schrodinger operator on the propagator, let me just shorten this. And so the Schrodinger operator is minus I h bar d by dt plus h squared by 2m grad squared minus v of x. If I apply it on k, xt, x prime t prime, or t0, whatever you want to call it, then this satisfies the Schrodinger equation except for a contact term. Okay. So there are different ways of showing that this is true, but what we shall do is that we shall show that this is true by solving this equation explicitly, okay? So let's take K and make a Fourier transform, okay? So we're going to do a 4-dimensional Fourier transform. So we'll have dE and d cubed P. And then we have some constant, it's something like this, but the precise power of this is not important, and I might make some mistakes there. Times E minus I epsilon by H bar T minus T0 plus I P by H bar X minus X prime. Maybe I should use be consistent and use T prime here. And then the Fourier transform tells me that there should be a kernel like this, which is a function of epsilon and the 3 vector P. Is this clear what I'm doing? I'm just taking a Fourier transform, a 4-dimensional Fourier transform. But is it obvious?
Yes, sir. Yeah.
Okay. Because I'm also taking a Fourier transform in the time direction. So you see that here E and P are unrelated variables. They're not necessarily, they have nothing to do with energy or anything initially. So epsilon and P are unrelated at this point. In physics parlance, we say that the particle is off shell. Okay, when the energy and the momentum of a particle do not satisfy the non-relativistic or the relativistic energy momentum relationship, we say that the particle is off shell. Okay, this is physics lingo. So now we look at the right side of this equation. The right side of this equation is the Fourier. If you look at it, do the Fourier transform of the delta functions. The delta functions have very easy Fourier transform. The kernels are they are just constants. So the right hand side is just e to the power minus I epsilon by h bar t minus t prime plus I p by h bar dot x minus x prime. Okay? You know this from the definition of the delta function. Is this clear?
Yes, sir.
Okay. Now let's apply the Schrodinger operator on K. So if I apply the Schrodinger operator, it has time derivatives, t derivative and x derivative. But this guy does not depend on t or x, right? So it's just going to come in, and there'll be one time derivative, and that one time derivative will bring down minus I epsilon h bar by h bar, and the two time derivatives will bring down I squared p squared by h bar squared, right? So as a result, on the left-hand side, apart from the integral and everything, but we will have epsilon, and then we will have minus p squared divided by 2m plus v of x. The v of x just goes on for the right. And then we'll have k tilde, which is a function of epsilon and p. And on the right-hand side, we'll just have 1. Is clear? Because what we're doing is that we are just getting rid of this integrals, of the integrals, right? And the exponentials. So this is what we get when we try to solve that equation using Fourier transform. So what is the solution? The solution is epsilon must be equal to 1 divided by, let's name this E, right? Sorry, so the solution is that the k tilde, which is what we're looking for, must be equal to E minus curly E minus E, right? But this is not a well-defined solution. Why? Because if I take this k tilde and I plug it into my integral over here, if I plug it into my integral here, so here I'm plugging in that value. If I do the integral over the epsilon, whenever epsilon becomes equal to E, what happens to this k? It blows up, right? Because the denominator becomes 0. So therefore, this solution is not well defined because this E integral is not well defined. So we have to specify how to do this integral.